gentlemen, boys and girls, welcome to the Hartford Astronomy Group. I'm Alan Willison, the chairman, and it's my pleasure to see you all here this evening. I know we've got one or two new people here, so for your benefit, one or two little rules to ask you. Could you please make sure your telephones are switched off? And if the fire alarm does go off, please exit through the doors at the end here and congregate on the car park where we can check that everybody is safe and sound. And welcome to those of you on Zoom. I know we've got some new people on there as well, so a very special welcome to you too. This evening, after these announcements, we'll have Martin, who will give us a talk about the night sky. And following that, Jerry will introduce tonight's speaker. There will be a chance to ask questions from the floor. You can ask them. Please wait so that we can bring a microphone to you so that everybody on Zoom can hear you as well. And for those of you who are on Zoom, if you want to ask a question or any problems arise during the meeting, please type in the chat facility and we'll sort things out from there. Okay, so after that talk, there's just a few announcements. I hope you've been reading the screen about next term, September. But those of you who are members, you don't need to book anymore. Just turn up. Visitors obviously will still need to book, but for the rest of you, you can just turn up. You don't have to do anything, and you can log in there. It would also give me a chance to say we've got a new committee member, Alana. Give us a wave. All turn round, stare and make her feel embarrassed. She is our new secretary and we're very pleased to have her on the committee, as we are all the other members. So that's enough from me for now. I'm now going to pass you over to Martin.
Thank you, Alan. Good evening, everybody. Been a few months since I've done this. Thank you, John, for standing in for me. Done a great job as usual. So I'm going to go straight into it. So here's the first one. SpaceX Falcon Heavy launch 25th of June. So anybody want to watch that? That would be quite interesting, I think. So we seem to be getting more and more companies, Boeing now, involved in sending satellites up and going to the space station. So it'd be interesting times coming, I think. So June solstice, longest day of the year. So I thought I'll do a little bit on this. I mean, I'm sure you all understand the nature the nature of the solstice, and it mainly means that because of the way the Earth rotates at an angle on its axis, 23 degrees and 4 minutes, that over a period of a year we tilt away or we tilt nearer to the sun. And at the moment, we are, within the next few days, going to come where the sun will be directly over the Tropic of Cancer, as I've shown on the image there. See if this works. Yeah. So there's the Tropic of Cancer there. So it means our longest day. And then in 6 months' time, we'll be down here where the tip of South America is, and will be our shortest day. So that's just a point of interest. Well, obviously for astronomers, we prefer the winter solstice because we get much longer looking up in the sky, not the 2 or 3 hours I've got currently to do any imaging. So just going to the moon next, first quarter moon. So that's on the 14th. So it'll be quite a nice time to view the moon because you can see there that the terminator, which is the line between here, between the edge of the moon, and it shows up a lot of the detail we get from the craters. So if you've got a telescope or a pair of binoculars, it's a good time if we've got a clear night to get out there and have a look. Okay, so now we moved into summer, and I just want to point out the summer triangle. So it's just an image. I mean, this is the meridian directly overhead. We have Deneb in Cygnus, and this is Cygnus, the swan. You can see the neck and the wings of the swan there. Vega in Lyra, and Altair at the bottom here, and this is what we call the summer triangle. So I'm really going to try and concentrate on this area of Cygnus at the moment because it's in the middle of the Milky Way. So we get a lot of nebulas, a lot of activity going along here. So it's quite interesting. So I'm just going to zoom in a bit. So here we have the neck of the Swan here coming out. There's lots of nebulas here. We've got a supernova remnant down here called the Cygnus Loop, which you can't quite see. You've got the North American Nebula here. There's other nebulas here. But the one I'm concentrating on at the moment is about a third of the way down the neck, which is the Crescent Nebula. Now, the interesting thing about the Crescent Nebula is it's actually a star, a Wolf-Rayet star, which is burning hotter than most stars. It's a massive star and it's burning very quickly, and its gravity is unable to keep its material. So this material you can see around, you can't actually see the star, this image I've taken the stars out, but all this material that's around the outside is come from the star, which is not exploded, it's still burning away. It will go supernova eventually, but you can see the material around here, which is all star making material. It's all gases that are in the area. But I wanted to talk a little bit about imaging because that's something that I'm into in a big way. So this particular image has been taken on what we call a mono camera. So it takes just black and white. And to get the colour, I have to use filters. So I use hydrogen alpha, oxygen 3 and sulfur 2. And they only allow wavelengths at 3 nanometers width to come through. And the colours we call false colour because I'll use whatever colour we're going to bring out the detail. This particular palette is called the Hubble palette because Hubble was the first to use it. So again, I was talking about a short period of time. I only got 3.5 hours, I think, imaging to get this image because it doesn't get really dark until midnight, and then 3 a.m. the sun's coming up. So, but I wanted to just talk about this particular imaging we're doing because this next image by Steve of the same target is taken with a one-shot colour camera, and you can see the differences in the colours. The interpretation is slightly different, but again, these are the two different types of imaging this sort of nebulas and things is to either use a one-shot camera. This is a CMOS camera, which is a much quicker, faster, more modern camera, so you can get a lot more shots done in a shorter period of time. And Steve's put a little bit of information about how he's actually captured that, which is quite interesting, and how he's had to balance it to get the stars correct and nice and sharp. So we had a lot of people taking images of the Aurora Borealis, so I thought it'd be right to put some shots in. Unfortunately, I wasn't well enough to participate in this, but I've used some pictures that Steve's put up. So here we can see the sunspots and the ejection from the sun, which has created the Aurora Borealis as it comes out from the sun in solar wind. It reacts with our magnetic field and produces these wonderful colours, and these all represent the different elements in our atmosphere and give off these different colours. So the images from the sun were taken from Steve's back garden by his 100mm refractor, and then using his mobile phone over his house, pictures of the Aurora Borealis. So there's another image just to highlight the narrowband image. This is one that I took earlier in the year, but I've just reprocessed it to bring out a bit more detail. It's the it's a Rosette Nebula, which isn't really visible at the moment. So this was taken, I think I took this probably about February, with my Vixen 103 millimeter refractor, and using my QSI camera, which is a mono camera, and the 3 nanometer bandwidth filters. So moving on back to the sun, seems to be another really good image, and this was taken at the same time that we had the aurora borealis, and this was taken by one of our astrophotographers, Michael. And I've just put a little bit of information about the reasons that we get the aurora borealis, and it's caused, say, by the solar wind. So the solar wind is radiation given off by the sun, and there's a full bandwidth from radio waves, which are really long, right up to the more energetic wavelengths, which are subatomic, and those are the ones that react with the atmosphere and give us the colours. Another image by Steve, which I thought was very good. This is a galaxy. It's an interacting galaxy, M51, known as the Whirlpool Galaxy. And you can see there we've got 2 separate galaxies, and the gravity between the galaxies, this spiral galaxy is taking material from this galaxy here. As you can see it being pulled across. These dark lines are the dust, mainly hydrogen. They've been drawn. These 2 will merge and become one galaxy in the end. So I put a bit of information about the distances. So it's 7.22 megaparsecs away, and it's 23.5 kiloparsecs in diameter, so it's quite a large spiral galaxy. It was one of the first known Messiers galaxies to be discovered. So Steve's taken 3 nights of data to achieve that image. And last image of the night, which I think is a nice picture of the moon, especially if we've got this quarter moon coming up shortly. Sorry. You can see here the craters that you should be able to see when you've got a quarter moon, or when you've got this terminator running through the centre of the moon here. So this is several images that have been pushed together, that Steve's stitched together to make this composite picture. So a lot of frames gone into this, but the results are spectacular. The definition was absolutely fantastic. Thanks very much. Thank you, Steve.
Right, thanks very much, Steve. So for our final speaker of our season, I always like to get a big name, and I'm delighted that we have Andrew Coates with us tonight, who has been president of the Society for Popular Astronomy. I've known Andrew for, let's just say, quite some time. His main work has been at the Mullard Space Science Laboratory, where, amongst other things, as you'll see from his opening slide, he is working on the ExoMars rover, the Rosalind Franklin rover, as it's now being named, which was supposed to have been launched a few years ago, but the activities in the Ukraine put paid to that. So a new launch adapter is being designed and built for it to go on an American rocket. Amongst other things, Andrew is in charge of the PanCam, the panoramic camera, which is going to help us see some incredible pictures of Mars. But the European Space Agency hasn't, I believe, offered a chance for people to have their names on the spacecraft, unlike all the American ones. No. Anyway, there's still a chance. So talking about life on Mars and also elsewhere in the solar system, particularly moons of Jupiter, will you please welcome Andrew Coates.
Okay, well, thank you very much for the kind introduction, Jerry. And so I'm going to talk to you about looking for life on Mars. and also something about Jupiter's moons as well. So as Jerry says, I'm from the Mullard Space Science Lab, which is, by road it seems about 75 miles away, which surprised me, but the software I was using took me that direction to come here, I think to avoid some of the traffic. Not all of it, but nevertheless managed to arrive on time. So, and on the right-hand side you see the Rosalind Franklin rover. So that is going to Mars now in 2028, as Jerry said. So we're very grateful to the UK Space Agency for the funding for this, and that's our Twitter or X thing these days it's called. Also the Centre for Planetary Sciences at UCL Birkbeck. So we'll talk about that. Okay, so just to start off a little bit about, oh, and I should say actually the logos at the top, these are relatively new. So these actually have NASA on it. So as Jerry said, we're now working with NASA. So just a few weeks ago, actually, the contract was signed with NASA to that they will provide the bits which they need to do. So they're providing a launcher, also providing the rockets for the landing system, and also providing the radioactive heating units for the rover itself. So those are the three things that we need from NASA. Yeah, it was real pain actually, you know, when the invasion happened. That was just at the end of the week where we'd done all the camera alignments and were just about to pack up to go to the launch site, and unfortunately the invasion happened. So that meant that we had to change partner for the mission. But anyway, it now says NASA on the logos, so that's fine. Okay, okay. So a bit about why we're interested in looking for life on Mars. So obviously, what we've got on here is a number of the locations in the solar system which are the sort of top candidates really for life beyond Earth. Of course, at the moment, we only know of life on Earth. That's the only life in the universe that we know of. So the top left, obviously, that's Mars. That's about half the size of Earth. That's very important because it means that it lost its heat of formation at the beginning of the solar system much more quickly than the Earth did. The Earth's bigger, and that's a bit like a large, you know, bath of water, and comparing that with how quickly a cup of coffee cools off. So Mars cools off a lot more quickly at the beginning of the solar system than the Earth does, and so that means that that can stop the motion of the dynamo, the iron which moving around inside Mars, like we have on Earth. So on Mars lost its magnetic field because of that cooling off. There may also have been a collision involved in doing that as well. So it lost its magnetic field about 3.8 billion years ago. So the size of Mars is very important. Because of losing that magnetic field, Mars has lost a lot of its atmosphere. The solar wind was mentioned earlier. That's a stream of charged particles, so it's positive ions and negative electrons coming away from the sun, about 1 million tons per second all the time coming away from the sun. Rather gusty, so you get these events which caused the aurora recently. We also had that down in Surrey as well, so that we've got some amazing pictures too. And of course it was seen very far south actually, down to Texas in the States, and you know that sort of latitude. Pretty amazing set of circumstances caused that, including the event on the sun, which we saw, and the 6 different events which caused the coronal mass ejections to come out, eventually to interact with the Earth. The fact that the interplanetary magnetic field was southwards means that was very good coupling to produce the magnetic reconnection in the day side and in the night side of the Earth, and that's what causes ultimately the aurora. Shooting particles towards the atmosphere, and those particles are what cause the aurora. So on Mars lost its magnetic field, so it lost its lost its protection from the sun and from the solar wind, and also from solar energetic particles and also galactic cosmic rays. So now the atmosphere of Mars is about 1/100th of the Earth's atmospheric pressure. So it's a very low pressure atmosphere, which means that the surface is sort of bathed in radiation, but also bathed in ultraviolet. So ultraviolet, of course, is harmful for humans, and so it's a bit on Mars, be like living under an ozone layer all the time, an ozone hole all of the time on Mars, and that means that Mars, the surface of Mars, is very harsh. So actually, on the sort of day side of Mars, on the warm sunlit side of Mars, it's maybe 5 to 10 degrees centigrade, something like that. But on the night side, every night it goes to minus 100 to minus 120 degrees centigrade. So anything you put on the surface has to survive that. The atmosphere of Mars is very thin, and so you don't get the sort of protection that the Earth's atmosphere gives us, for example. So Mars, 3.8 billion years ago was a different place, and we think that's when life could have happened on Mars. Probably is not there now because of this very harsh condition. And certainly, underneath the surface would be the best place to look for signs of life. So the other places on here, so Europa, of course, one of the moons of Jupiter, about a quarter of the size of the Earth. But the key point about that is this is an icy surface, an icy moon of Jupiter, orbiting at something like 6 Jupiter radii. It has underneath the surface a liquid water ocean. It's salty, and so that's from data from the magnetometer from Galileo, for example, has shown that, the Galileo mission which orbited Jupiter. So this is one of Jupiter's moons, and it is the favourite in the Jupiter system for potentially harbouring life even now. So the reason for that is, even though it's very close to Jupiter and the surface is bathed by the radiation belts of Jupiter, underneath the surface, there's enough radiation shielding that the ocean is well protected by that. The ocean, we think, also is in contact with silicates, so rock at the bottom of that ocean, according to combination of the magnetometer data and models. And so that's the only moon in the Jupiter system which is like that. So other moons there, so we have Ganymede, of course, the largest moon in the solar system, which has its own little magnetic field. It also has a water ocean, but that is in contact, we think, with ice. And the same with Callisto, very old surface, but Callisto also has a liquid water ocean and in contact with ice there. So Europa is our best chance, probably in the Jupiter system, to potentially have life. So Io, of course, is the closer moon. That has sulfurous volcanoes going off, about a ton per second of volcanic material going into the Jupiter environment, and we have the Io plasma torus, and this is filling the magnetosphere of Jupiter as well. So the JUICE mission is actually off to do that. So I was lucky enough to be on the science definition team for JUICE a few years ago, about 10 years ago actually, and so JUICE is now on its way and was launched last year and on its way to Jupiter. It will do a couple of flybys of Europa on its way also to Ganymede and Callisto for flybys, and then eventually it will go into orbit around Ganymede. So that's the first mission to do that, and I'll talk more about that mission later. So at the top right here, we have another sort of really prime candidate for life in the solar system. So Enceladus, this is one of the moons of Saturn. It orbits Saturn at about 4 Saturn radii. It's much smaller. It's about 1/25th the size of Earth. 250 kilometers radius, so would fit inside the North Sea. You wouldn't want it in the North Sea, but it would fit. And so Enceladus, the surface of that, again, we can see this is very icy. So from previous missions, the Voyager mission, especially at Jupiter, showed a very bright, in fact, very high albedo, one of the largest in the solar system at Enceladus. But we had no clue or no idea really that there was a subsurface ocean there until the Cassini-Huygens mission got there. So Cassini-Huygens, which we were lucky enough to be involved with as well. So we built the electron spectrometer, which is part of the Cassini plasma spectrometer. So with that we did a number of measurements, but the magnetometer instrument first found hints of an atmosphere at Enceladus, which turns out to be the plumes which we see, because of course having discovered that, the project went back and, we did a number of flybys of Enceladus, closer and closer, and actually the closest flyby, only 25 kilometers from the surface of Enceladus. So really daring mission. So JPL agreed to do that. And so And with putting all that data together, we now know that there are plumes of material coming away from Enceladus from a subsurface ocean. It's a global subsurface ocean. And not only is there water coming out, but there's also inside the water, there's small, and we see that actually with our electron spectrometer as well. We see negative ions, which are clusters of water coming out of Enceladus. But we also see silicates, so those are seen in the dust data. That is, again, sort of sandy stuff. So that could be signs of hydrothermal vents on the sea floor, as it were, of Enceladus. So again, it's a water ocean and in contact with rock or silicates at the bottom of that ocean, and so that's a sign perhaps of hydrothermal vents. There's sodium in the vapor as well, from sodium chloride, so that's salt, obviously. So salty ocean, direct evidence for that, and then the hydrothermal vents. There's also hydrogen coming out. So seeing that is interesting, because that's one of the things you need for life. So you need CHNOP and S. I'll talk about that bit more in a minute. Carbon, hydrogen, oxygen, nitrogen, phosphorus and sulfur. Those are the things which you need. And so we see all of those actually, there's evidence for those at all of these three objects. So Enceladus has sort of really joined Mars and Europa as prime places to look for potentially life within our own solar system. Also on this slide is Titan. So Titan is, again, this is an image from Cassini, and this is what you get when you don't just look in the visible, as they did with Voyager, which showed a very hazy atmosphere. But with a combination of infrared and ultraviolet, you can peer down to the surface. And so that's what Cassini was able to do. This is about a 25th the size of, 2.5th the size of Earth. So relatively large. You can see a haze around Titan. Titan is the only moon in the solar system with a really significant atmosphere. So this is like 1.5 atmospheric pressures that we have on Earth, but it's made of mainly nitrogen and a small amount of methane. So that means that it's a sort of a really amazing place for making hydrocarbons. And with our electron spectrometer, we found really heavy negative ions, which are prebiotic molecules actually in the atmosphere of Titan. So that was one of the really surprising results that we got from the Cassini orbiter, and from our instrument in particular. So Titan, though the surface is very cold, so minus 180 degrees centigrade on the surface, so not really suitable for life now, but again it has a subsurface ocean. But the amazing thing about Titan is the surface temperature is round about the triple point of methane, so that's where methane can exist as a solid, liquid and gas. So you have weather systems which are driven by methane on the surface of Titan. So it's not suitable for life as we know it, and it's very cold on the surface, and that's what causes that triple point. But nevertheless, it's an interesting location. So it's still on this slide as somewhere where potentially there could be life. And actually, this might be life waiting to happen in about 4 billion years, when the sun runs out of its hydrogen fuel and starts burning other things to do its fusion. So the fusion thing changes. The sun becomes a red giant, engulfs the Earth. It will engulf the Earth, but in 4 billion years, we don't have to worry about it immediately. So, but at that time, the outer solar system will be warmed up, and so Titan perhaps is something waiting to happen in the future. So also on this slide is Venus. So a few years ago, during the pandemic actually, there were some observations of phosphine in the atmosphere of Venus. The atmosphere of Venus that you see from spacecraft, like we have on the slide here, is clouds of sulfuric acid, and so you can see those V shapes due to the super rotation of the atmosphere. It's a very slowly rotating and the wrong way round rotation compared to other planets. But we can see the interesting cloud structures. But in those clouds, you not only have sulfuric acid, but apparently signs of phosphine. Now, this is still a controversial result. I mean, there are some measurements which seem to show maybe it's not that, and it's difficult to analyse the data. Anyway, it's still on the slide, and that's why there's a question mark. It's a possibility, but you know, there are still some scientists who think that Venus could be a place which is worth looking for life. And of course, as mentioned on here, extrasolar planets. So, you know, if we can do things in our own solar system, we can observe extrasolar planets with things like JWST, but also other telescopes in the future, Ariel included, which will be looking at extrasolar planets, and Plato. But those will, you know, if we find life in our own solar system, then that sort of begins to tell us about what to look for in extrasolar planets. And so this is why it's important to explore our own solar system as well. But the extrasolar planets are also extremely interesting, and potentially, you know, the search for habitability in an Earth-like planet and extrasolar planets is an interesting endeavour. Okay, so we're talking about Mars tonight, though. So Mars, 3.8 billion years ago, might have looked like something on the left. So this is a bit Earth-like, isn't it? So 3.8 billion years ago. Bear in mind the solar system is 4.6 billion years old. So this is quite far back in the solar system's history. This is the time, the end of the late heavy bombardment, and this is about the time when Mars lost its magnetic field. So after that, this started to be stripped away. But you can see, you know, on the surface there may have been lakes and maybe even seas. There's water in the ice caps as well, water in the clouds. So that is what models tell us, and also the MAVEN spacecraft, which is at Mars at the moment, and Mars Express has given us a lot of data on this as well, about how that solar-wind interaction works and how the stripping of the Martian atmosphere is working now. And you use that to extrapolate back to what conditions might have been like this time 3.8 billion years ago. And the interesting thing about this time is this is when life was starting on Earth. So we have a habitable environment at a time that life was starting on Earth, so maybe it could have started on Mars as well. This is why we're interested in looking at Mars as a potential place for life. So on the right-hand side of the picture here, you have a picture of Mars now. So this, of course, is the dry, cold desert place that mentioned earlier. So very harsh surface conditions now, and this is why we want to drill to look for signs of life. Okay, so the difference of Mars then and now. So first of all, there's lots of evidence of water having been on the Martian surface. So this slide actually is from the Mars Express spacecraft, the high-resolution stereo camera on that. This is a stereo rendering of that data. And this is just one example of an old water feature on Mars. There's lots of evidence, beginning with the Viking orbiters in the 70s, and then all the missions since have discovered the presence of water, 3.8 to 4 billion years ago type of time, so in ancient surfaces on Mars. Also, Mars had a magnetic field, so the evidence for that comes from the Mars Global Surveyor mission. The first time a magnetometer was taken close enough to Mars to be able to do a good survey of the Martian environment. So on this map here, we obviously have latitude and longitude, but the color scale is height. So this is a height map of Mars. And you can see this is blue, relatively low areas, and then going through green and yellow to red to eventually white. White is the highest areas. So you can see the northern hemisphere, we have a relatively low environment, and there may have been a sea in that area. There's also the Hellas Basin associated with a very large collision which happened on Mars. But in the southern region, we have much higher areas. So this is the southern highlands of Mars. And when the magnetometer went to Mars, the magnetic field strength and direction was recorded. And what you see actually is these contours. And so the contours are in nanoteslas here at the orbit that Mars Global Surveyor was, so a few hundred kilometers above the surface. And we see white and black contours. So these are of outward and inward directed magnetic fields. So these are crustal magnetic fields left over from when Mars had its own global magnetic field. And they're concentrated in this region in the southern hemisphere. So this is the southern uplands. The dates of this terrain is about 3.8 billion years. That's where the 3.8 billion years comes from. You get that from counting the crater density or estimating the crater density from the craters on Mars here and using that to determine the age. And so we get that 3.8 billion years ago, rocks forming, etc., but and then trapping magnetic field left from an initial dipole magnetic field which Mars had. So that's the first evidence that that we had a magnetic field of Mars. And now we have these crustal regions of crustal magnetic fields. So that interestingly means that you get aurora on Mars as well. So that was discovered with the Mars Express spacecraft. So in between some of these crustal fields, in the ultraviolet, you get aurora. There's a chance that we may get visible aurora as well. And actually, when the solar event recently passed the Earth, we were looking with the Perseverance rover to see if we could see aurora from the surface, because there's a chance of seeing visible from the surface as well. But it was on the glancing edge of unfortunately, of the solar event which caused the amazing aurora that we had here, and you saw the nice picture of earlier. But Mars has aurora as well, and so but it's sort of defined by these crustal magnetic fields. Again, there is some atmosphere. It's not a zero atmosphere. It's 1% of the Earth's atmospheric pressure. So that's another big difference of Mars 3.8 billion years ago and now. So also there was volcanism going on. This is Olympus Mons, the biggest volcano in the solar system. You can see that on the map over here. So that is 600 kilometers across. It's a shield volcano. At that time, again, 3.8 billion years ago, there's evidence for that volcanism having been active at that time. And so that would have contributed to water cycles and all sorts of cycles that you can get on Mars, like we have on Earth with volcanism taking stuff up into the atmosphere, and then you get precipitation and so on. And the same thing would have been happening on Mars at that time. So 3.8 billion years ago could have been a good time for life starting on Mars. Okay, so I mentioned what do we need for life. So the sort of recipe for that, all of which were present on Mars 3.8 billion years ago, is liquid water. There's evidence for that on the surface with those flowing channels and so on. The essential elements, these have been found from a number of different missions. A source of heat is needed, and you need enough time for life to develop. So the only one we're not sure of was there enough time for life to develop on Mars at that time. But if it developed on Earth, it could have developed on Mars, etc. So it is worth looking. Okay, so missions to Mars. So these, you have chances to launch to Mars every 2 years because of the way the planets align, every just over 2 years. So in 2020, we had a number of missions launching. So the UAE had the HOPE orbiter. That's now looking at the atmosphere of Mars. China had the Tianwen-1 orbiter and also the Zhurong rover, which landed and worked amazingly well for a while. NASA had the Perseverance rover and the Ingenuity helicopter, which landed on Mars. And of course, the Ingenuity helicopter subsequently did some exploration in the atmosphere, which I'll talk about in a minute. 2022 is when we had hoped to launch ExoMars, as it was called at that time, now Rosalind Franklin. So that was the 2022 opportunity, would have been. This year we have the NASA are launching ESCAPADE, which is again a mission to look at escape, atmospheric escape at Mars with a limited payload, but nevertheless a 2 spacecraft mission at Mars to look at the solar wind interaction. In 2026, Japan is launching MMX, so that's going to be bringing samples of Phobos back to Earth. So that's interesting. Phobos may be a captured asteroid, so you'll be able to tell with lab-based experiments whether that's the case or not. And also, there may be bits of Mars actually on Phobos as well, created from collisions, and then material going from Mars itself to Phobos. And so again, a sample return from there will be very interesting in 2026. And in 2028 now we have the ESA-Rosalind Franklin mission. That's mainly what I'm going to be talking about tonight. So also operating at Mars, because Mars is a busy and interesting place. So there's Mars Odyssey, Mars Express, the ESA mission, MRO, the Mars Reconnaissance Orbiter from NASA, Mars Science Lab, so the Curiosity rover, that's still going well as well. Also the Indian Mars Orbiter mission, MAVEN, another NASA mission to look at atmospheric escape, and then the ExoMars Trace Gas Orbiter. So all of those working on Mars and producing exciting results. So of course the Perseverance rover is one of those things. So landed in 2021 after the 2020 launch opportunity. So there's Perseverance on the right, and the little helicopter. This is Ingenuity, the helicopter, and that's a picture kind of next to each other. A selfie. So how do they do that? I mean, in this case, what they did was use the robotic arm and take images at different locations to be able to get an image like that. But a beautiful image which shows you the situation on Mars. So I mentioned Ingenuity, the helicopter. So this was just check that's running. Yeah. So this is a video which shows the first powered flight and controlled flight on another planet. So it's a Wright brothers moment, they said, and they actually had a little bit of the Wright brothers plane on this. So there's the little helicopter taking off. So it's taking off in a very thin atmosphere. The rotor blades are counter-rotating at 2,400 RPM to be able to achieve that flight. So this was the first flight, and it went up and went down again safely. All of it looked at by Mastcam-Z on the rover, which is the camera system at the top of the mast. So we have a scientific involvement in that, but NASA, of course, doing that mission. Okay, so Perseverance is going very well. So how are they doing? So as of last night, it's actually traveled 28 kilometers across the Martian surface. It's taken a total of 24 rock cores, so 14 plus 7 plus a couple of other samples, and then some witness tubes and an atmospheric sample as well, but 24 actual rock samples. The helicopter did 72 flights, so that was the first one that I showed, but it actually did 72 flights. As of January this year, it stopped flying because unfortunately one of the rotor blades was damaged during landing. But 72 times, it was only expected to fly maybe a couple of times just to demonstrate the technology. So it's amazing that this did well. And it itself flew over 17 kilometers across the surface of Mars. So amazing achievement. And of course, this is where the rover is. And so this is an image just from today showing where the Perseverance rover is. So of course it's exploring a place called Jezero Crater, which is the signs of a river flowing into it and a river flowing out of it back in 3.8 to 4 billion years ago timescale. You can see the rim of the crater there. So the landing site actually was here. You can see the red things are showing where samples were taken along the route, and it was actually exploring this region here, which is the river delta of the stuff coming into Jezero Crater. And you can see samples being taken. It's now up on the top left position, the helicopter left behind, as you can see there. And this is where it is on the surface of Mars now. So it's about to embark on some exploration of the crater rim. So the rim of this large crater on Mars. This is a great location because orbital imagery and data have shown that this is a place where water definitely was in the past, with evidence for clays and so on the surface there. So this is one of the interesting areas to look at potentially for life. So it's collecting samples and putting them in tubes and caching them at a particular point on the surface, and also keeping some on board. And hopefully those samples will one day come back to Earth. But But there's a little video about the last sample which was taken, which is quite interesting, which I thought I'd play briefly, if it will. Maybe not. Oh well. Not going to play, unfortunately. Oh well, never mind. But it's about this the latest sample which has been taken, which is the 24th sample. It's been taken from a particular area which has got some white traces on the surface. It looks to be one of the most promising samples in terms of looking for life. So that sample hopefully will be brought back to Earth. Actually, if you go on the web, you can see this clip. It's got somebody explaining why that's an interesting sample. That's worth a look. Apologies it doesn't work, I don't understand that. Okay, however, samples. So samples have been taken by Curiosity, but by Perseverance. This is an amazing picture, which a lot of you will have seen the landing, I'm sure, of Perseverance in February 2021. So this is an image of the rover landing on the surface, sent back live. There was a video sequence as well, sent back live. This is the first sample, rock sample, which was taken and put into the sample tube. So as I say, these are kept, some of them on the surface, some of them on the rover itself. And eventually, the idea is to bring these back to Earth. And so we hope that the Mars sample return mission will be going. And these are the elements of it being shown on the slide there. So you can see the idea is for Perseverance, possibly backed up by another helicopter, would bring the samples back to this surface station. Those get put into the rocket here, blasted off into orbit, and in Mars orbit waiting for it is this sample return station, and then the samples come back to Earth. So this needs a couple of extra launches. So the Earth Return Orbiter, which the European Space Agency will do, that's one of them. The other one is the sample retrieval lander. So this is the lander system and with the thing which will take off from the surface of Mars. So this will be the first rocket fired from another planet as well. So again, historic in that sense. And the idea is to return these samples to Earth. So we'll see if this video works or not. I don't know what's happening with the videos tonight. Oh, that one's all right. So this illustrates Perseverance collecting its samples and then wistfully looking up in the sky for the lander to be coming down, which eventually will transfer the information back to Earth and the samples back to Earth. So here's the samples being put into this safe place on the rocket. And the part containing the samples then rendezvous with the orbiting orbiter, which will transfer the samples for return to Earth. That's the capsule which will return to Earth and bring the samples with it. Okay, so NASA and ESA are working together on this, and we're hoping that this works. NASA have had some budgetary problems with this particular mission, which mean that it's a challenge for them. So what they've currently done, actually, is to provide some announcement of opportunity for industry to come up with different ways of doing the sample return, which might hopefully be cheaper, because the budget basically has overrun what it had hoped to be. So we're hoping that Mars sample return will get approved at at NASA. ESA are already are working on it and with their parts, and so we hope that will maybe bring samples back to Earth in something like 2035. So middle of next decade. So the next slide actually shows the type of facility that we might be able to bring it back to. So this is Diamond on the Harwell campus. So you get an idea of the size of this from the cars in front of it and so on. So that is where, that's one of the potential places. It just really showing this is to illustrate we can do the types of things on Earth that you couldn't possibly hope to do on Mars in terms of analysis. And so having these large facilities, and this is only one, there's obviously the US and Europe and so on involved in this, and the samples would be shared around, but this is just an example. Okay, so hopefully that will go well. In the meantime, so we do have the Rosalind Franklin rover, so this now is launching in 2028, landing in 2030. So this is our rover, built at Airbus in Stevenage, so not too far from here. So here is this is the drill on the front, wheels, of course, solar panels. So that drill has drilled underneath the surface up to 2 meters and bringing samples to be put into the analytical drawer, as it's called, and that inside the rover, the analysis is done and sent back to Earth. So we're not bringing these samples back to Earth, we're analysing them on the spot. But the really different and new thing about this mission is the drilling 2 meters. That's the important thing, getting underneath the surface. And we have both context and analytical instruments to do the analysis of these samples. So the context sort of helps you decide where to drill. Now PanCam, that I'm the lead of, is one of those context instruments. And then we have analytical instruments also to analyze the samples. So we call it Rosalind Franklin. So why do we do that? So this is named after this amazing X-ray crystallographer who took a particular photo 51, using X-rays of a fiber of DNA. And that was fundamental to Watson and Crick's discovery of the double helix of DNA. So the UK Space Agency actually had a competition to name the rover a few years ago, and they had 36,000 entries for that competition, which was pretty amazing. I think they only had 6,000 for Tim Peake's mission, but that's another story. But nevertheless, that came up with Principia, which of course another great name. In the case of Rosalind Franklin, so this is why the rover, this name won as the potential name. There were other examples like Rover McRoverface, things like that came in, but this one was a much more, much better name. So she unfortunately didn't share in the Nobel Prize. I think she didn't live long enough to do that, sadly, because she died young. But the discoveries were critical to that discovery of the double helix, and that's why this mission is named after her now. So ESA call it the Rosalind Franklin mission, brackets ExoMars. But she did lots of other important work on the discovery, on the structure of carbon, on viruses and so on. So very important set of work, and that's why it's appropriate to call it after her. So why do we need to drill deep? Well, in the first few first bits of the Martian surface, it's harsh for life. So as I said, the surface is very harsh, but we do have penetration of things which are destructive for life, so organic destructive agents. So we need to drill below about 1 millimeter to get below where ultraviolet gets to. So that's the thing which bathes the planet, because that thin atmosphere, that's harmful, hard ultraviolet radiation getting to the surface. That's not good for life at all. So if you drill about 1 millimeter, you get below that. Get below oxidants, things like perchlorates in the surface area of Mars, which are not good for preservation of the species either, causes chemical problems. And we need to get below about 1.5 meters, where ionizing radiation can penetrate to. So we had a student a few years ago, now a professor, but working on he was working with us on looking at the radiation environment on Mars and how far you have to drill. And so 1.5 meters is a good depth to be drilling, to be looking potentially for signs of life or for biomarkers. Drilling deep is important. So this is why this mission still holds an important place in Mars exploration. Even though it's delayed until 2028, it's still going to be very exciting. So this is our strategy with the surface instruments, to find good outcrops and then drill below the subsurface to get rock samples from below there where they have the best chance of being preserved, and then analyse those on the rover. So where are we going to land? It's a different area to Jezero Crater is over here somewhere. So again, in the middle regions of Mars, between the sort of low northern plains and the southern highlands. Jezero Crater over on the left somewhere, but actually Oxyoplanum is where we're going to land with Rosalind Franklin. So that's been chosen. First of all, the engineering constraints on landing give you some constraints, but also scientifically this area is good because of signs of water. So from Mars Express data, which did a lot of mineralogy, we can tell that there are clays on that surface in this location, which is a really good location. It's slightly older than the Jezero Crater landing site of Perseverance, so again, that is potentially an advantage as well. But as I say, the key new thing is we're going to drill underneath the surface. These are the old landing ellipses from the previous mission. The azimuth of that will change a bit with the 2028 mission, but roughly it will be in this sort of area. Some very detailed mapping have been done by colleagues. So Peter Forden, especially from the OU, has done some very interesting mapping work. Actually had the whole ExoMars team working with him on this. So a number of us actually helped to do that. Map a couple of years ago, so that's published, and which gives you the sort of geology of this area, which looks very interesting. Okay, so what about the instruments? So we have, as I said, context instruments. So those are on the left here. So we have PanCam, which is our wide-angle stereo camera and a high-resolution camera as well. So that is our instrument. So that's the one which I'm leading. So we have 2 wide-angle cameras and a high-resolution camera. This gives you effectively the geological context for the mission. So we used to have a Russian instrument which was going to do infrared, but now we have a UK-led instrument for that. So that's the ENVIS. That is Welsh for rainbow, led by my colleague Matt Gunn at Aberystwyth University. But we are helping actually to build the sensor system, our lab, and then Rutherford Appleton Lab are helping with the electronics for this. So it's now a UK instrument actually. So we now have 2 UK instruments on the rover. This was announced as of last November. We got the money for it and so on, and we're starting to do the detailed design for that. And my colleagues that have helped build PanCam are now working on ENVIS. So it's a really good thing that we have that, again, for the launch in 2028. The third one here is Wisdom. This is a subsurface sounding radar. So you're looking for outcrops underneath the surface, also water underneath the surface. There's a close-up imager with which you're able to look very closely at rocks, even closer than we can look with our high-resolution camera on PanCam. So this is like a geologist's field lens looking at the surface. There's a little visible and infrared spectrometer inside the drill tip itself. So that gets you the local geology from where you're getting the sample from underneath the surface. And then the analytical instruments as such are inside the rover. So there's 3 instruments there. There's Micromiga, which is a visible and infrared spectrometer looking at the samples. The Raman spectrometer is Spanish-led, but involves the UK as well. So Leicester University and also Rutherford Appleton Lab again are involved in that for and produce some of that. But the PI is actually Spanish. But that's the Raman spectrometer. So with that, you shine a laser at the sample, see what comes back, and that tells you about mineralogy. And so that uses Raman spectroscopy to do that. The other instrument is the Mars Organics Mass Analyzer, and this is why NASA is still interested in this mission, because NASA are involved in building this. So this is the thing which is, it's a gas chromatograph mass spectrometer, the type of thing we had on Beagle 2 from the OU, but this is a more developed version. For example, it can do chirality determination. So this is looking at left-handed and right-handed molecules. One of those is used by life, and so that's this is the first thing to Mars actually which will do that. So, so this instrument, the PI is German, but also France and NASA involved in that, and so this is a very exciting instrument. So with that, we'll be able to look at basically biomarkers and detect biomarkers if they're there. Whoops. Okay, so this slide shows the rover itself, and so the rover, as I say, was built in Stevenage, the rover itself, but some of the testing was done elsewhere. So this is in Toulouse, in the Interspace facility there, for those of you that know it, and this is the rover. It's a 300 kilogram rover. There's the mast with PanCam at the top of it, the solar panels which you can see there. And you can just about see, this is our PanCam calibration target here, which you can see on this as well. And then there's a rover inspection mirror at the bottom. Here are the wheel, you can see that. And then there's the fiducial markers on the side. So with all that, and PanCam, the image at the top is taken in our clean room at MSSL. We had to keep things very clean. The last thing you want to do is take life to Mars and measure that. You have to make sure that it's clean enough to be able to do that. So we're sending swabs away to be analysed every week during the build and assembly process. And that's a picture taken in our clean room, and that's the flight model actually on the flight rover. So that was the rover together actually in 2019, and subsequent testing was done at Thales Alenia in Italy. So they are the prime contractor for the whole mission, but Airbus with this lead role in actually building the rover. So very exciting for the UK. Okay, so with PanCam, we've put as much science as we possibly can into what is basically a camera system. So we have the two wide-angle cameras, as I said. So those are separated by 50 centimetres. We have our mast means that we're about 2 meters above the surface of Mars. So we get very good stereo reconstruction from those two eyes. Each of the wide-angle cameras has a filter wheel, which has 11 positions on, and these are the actual filters going to Mars. So they're on the flight model now, and that is the face which will be looking at the Martian surface. These are the filters in nanometers. So obviously you can see we have red, green, and blue for color, getting that right. Then we have a number of geological filters, which are the sort of fairly narrow filters there. And then we have the very narrow filters, which are the solar filters. So I'm sure a lot of you use solar filters, but in this case, we're looking especially for a water absorption feature at 935 nanometers. And so with that and looking at the continuum nearby, we can actually work out that, that composition. So one of my PhD students was working on that. She actually passed her viva last Friday, so that's really good. Another ex-PhD student actually helps us to choose the geology filters. There's another one that's been working on dust storms. She graduated a couple of weeks ago as well with her thesis and successfully got through her viva. So we've had a lot of students working on this through the years as well. And that water vapor content is what we can look at with the water filters. And the way we do that is to look at the sun with the camera and towards sunset and looking at how deep that dip is. And that's what Priya was working on for her thesis, one of the things. And then with that, you can work out the water vapor content in the atmosphere, how much water there is in the atmosphere, and then expand the model, and then see that water escape into space as well further up. So it's a very connected system. So we have also a high-resolution camera, colour high-resolution camera, which provides rock texture. So that just has a very narrow field of view, a 5-degree field of view, and has high resolution, high enough to do the scientific objectives that we want. Okay, so we've had a number of field trials and things which we've done in the past. That shows the Aberystwyth PanCam emulator. So this works very much like the real PanCam. So you can see there are 2 wide-angle cameras with the representative filters, and also a high-resolution camera on board. So all together, you know, it emulates this really powerful camera system which we have going to Mars. So these are just a couple of the examples of the analysis which we've done with that. So this was a particular feature, and you can see the 3D imaging has been done, but also geologists have added what's called dip and strike. So that's looking for sedimentary rocks and looking for the sort of history of the environment there. With the composition, we can also look at principal component analysis. So with that, we're looking at ratios of filters one against the other, and with that you can work out mineralogy. So you can see what's gypsum, what's sulfur, etc., as to those show up in different places on this. And so another previous student actually went to Iceland and did some work there. So the emulator actually has been all over the world to various different Mars analog sites. To be able to do that, to be able to do this type of analysis. And this is just an example of some data taken in the Atacama Desert in Chile, which again is one of the most interesting sites for, for Mars analog work. Okay, so this is a picture of a colleague, Matt Gunn, who's been working on the calibration of PanCam, but he's also now PI for the ENVIS instrument. So he was in the Airbus clean room when the rover was there, holding up a piece of paper for our first test on Mars. And so the first light on Mars, the first PanCam image, it says "Hello Mars." So this went successfully all through the system. So we were very happy that happened back in 2019. We had hoped it would get to Mars by now, but anyway, it hasn't yet. Okay, so what has been happening recently? So this is another model of the rover, which actually is in the Altec Mars terrain facility. So basically a sand pit. So there is one, or there was one at Airbus as well, but this is the one in Turin. And you can see the gravity is simulated by having those ropes. So this is doing drilling tests as well as roving around and looking at the terrain and so on. And you can see some of those in the background here. So there's PanCam looking down at a target. That is the Russian instrument which we've got to replace with the ENVIS instrument. So it's got to be no bigger. It's got to be exactly the same mechanical and electronic interface to the rover. It's got to use the same harness all the way down to the electronics. So it's a tough job, but we can do it. And this is. However, we've got to do it by 2026, and so that it gets on the rover ready to be sent to Mars. And so that's the challenge at the moment for our engineers and also the Aberystwyth and RAL people. So very exciting that we've been able to add that, because of course that really adds to the science of PanCam, going into the infrared with a few pixels of the high resolution camera, and we're able to get spectra there. Okay, so this is again a little video. It's interesting, most of them work. But okay, so this is a 3D rendering of that terrain inside the Mars terrain facility in Turin, showing the really good stereo reconstruction we get. These bars are 1 meter and then in 10 centimeter graduations there, and that's the terrain in that room. And so we recently used that for some data compression testing. Okay, this image actually is from a test last year where this was a drilling test. So getting the drill sample from I think that was from 1.7 meters underneath the surface in this case. And you can see this is being imaged by our high-resolution camera, because we can see from the top of the mast, we can see the analytical draw, and you can see that's now you have it, now you don't, the sample before it's taken into the analytical draw. Okay, so this actually is another video, which we'll see if this works as well. So this uses the latest renditions of what the rover will look like on the surface. Descending and landing system with heat tiles and then parachutes, and eventually rotor rocket system, including that landing system actually built at Airbus as well. So very exciting. Getting the samples, and then eventually, hopefully, finding signs of life. So they're releasing videos bit by bit of what the rover is going to be like going across the surface. So I mentioned the landing system. So the landing system itself is being built in Europe, in Airbus, and then the retro rockets which stop it hitting the surface, those are from the US. So, but again, very exciting mission. Okay, so a summary of the Mars part of this then. So we're in a golden age really of Mars exploration at the moment. So Hope and Tianwen-1 and Zhurong, but also Perseverance and Ingenuity, all these arrived in 2021. Perseverance has cached samples which are only 6 centimeters actually, but they drill into rock, so it still will be really valuable. They're cached on the surface, ready for Mars sample return, and hopefully that will work. But this decade, we hope that Rosalind Franklin will be launched to provide an important new dimension on Mars, drilling underneath the surface. And this is some of our team. And I should say, you know, we have a big team working just on PanCam, and these are some of the institutes involved in that. We have a 9-nation science team, but these are some of the people who've been involved in the hardware and the science and so on. So briefly about JUICE. So I mentioned JUICE earlier with the possibilities of life on Europa. But of course, the point of this is to eventually go into orbit around Ganymede. Io there in the distance. Again, that will be studied from a distance. And there's Ganymede, but Europa and Callisto, there'll be flybys of all of those, but then it will go into orbit around Ganymede. And this will be complemented by Europa Clipper, the NASA mission, which is going later this year. So this mission was launched in 13th of April 2023. So it's great to see that all that work we did 10 years ago to define the mission, 10 to 12 years ago, has come to a real mission. We actually chose this JUICE name after several gin and tonics in the evening, after one of the intense meetings that we were having at the time. But it stuck. So Jupiter Icy Moons Explorer is what it's short for. So launched on 13th of April last year. Arrival at Jupiter in 2031. There'll be flybys of Callisto, Europa and Ganymede before orbiting Ganymede in 2034. So very exciting, and that will be looking at, for example, why does Ganymede? It's the only moon with a magnetic field, so that's really interesting thing to look at, and also looking at habitability on the other moons too. Also Europa Clipper, so that's launching in October this year. That's an image of what the spacecraft is like and the trajectory which it's taking to get there. And with this, we have up to 50 flybys of Europa in the 2030 to 34 time frame. So there will be some overlap with JUICE, which is great, and that will provide some amazing data. So looking for habitability and so on. It's not looking for life at either of these missions, but looking for habitability and the conditions which might lead to habitability. So thank you very much. I will stop there and see if there are any questions. Thanks.
thank you very, very much, Andrew. A really exciting preview of missions to come, and we really look forward to seeing that. And I'm hoping, actually, where actually it is the rover at the moment? Is
Turin.
It is in Turin.
Yeah.
But it will be coming back here, won't it?
No, it won't be. So, so the testing has been done in Turin. It's basically ready to go from there.
So they've completed all of the testing in Stevenage.
Yeah, that's all done. That's all done. And but what they're doing at the moment, of course, in Stevenage is starting to build the landing system. So it's great to have got that contract as well. Actually.
That is excellent.
Yeah.
Yes. Yeah. Okay. Because obviously that is an extremely major part of it. Right, do we have any questions from within the room? All stunned. Any online?
Yes, we have one online.
Okay.
Okay, so this is from Peter Jenkins. Thank you for such an illuminating presentation. If the costs and challenges of retrieving samples from Mars are such that we won't see any data for many years, could advanced analytical tools be developed and sent to Mars to analyse samples in situ and transmit the data back to Earth?
Yeah, good question. So this is, of course, what we're doing with Rosalind Franklin. Yeah.
Sorry, can I just finish the question?
Yeah.
And to analyse new samples as they are collected in the future, perhaps useful and cost-effective for landings on other planets and their moons.
Yeah. So yes, it's certainly interesting to try to do that. I mean, there are plans for other missions. So after the Rosalind Franklin and Mars sample return, which NASA and ESA are doing. As well as that, there is a Chinese Mars sample return, which hopefully that will be launched in 2030 as well. So that will be interesting to see which samples get back first, actually. But the Perseverance sample's been very carefully chosen to bring, not just any sample back, but to have this multitude of samples which will be brought by the mission. So hopefully, if the cost is done, so those are the kind of current missions which are planned for Mars. Yes, there are proposals to have another set of missions, actually orbiters, which ESA would have to Mars, and so these would use electric propulsion, and there may be chances to get passenger payload on board. So there's some studies going on that at the moment. Other objects as well, yeah. So Europa obviously is one of the other prime targets which are of interest, and so there are some mission plans for that, as well as Europa Clipper. And I think until we get the results from Europa Clipper, further Europa exploration might be sort of wait until then. But Enceladus as well, and I should have mentioned, actually, the European Space Agency recently finished its study of what the next large mission might look like. And so one of my colleagues was involved with that. With that is now going to be a mission to Enceladus. So we're hoping that ESA actually will be going to Enceladus to follow up that really, important third strand in the solar system for potential life there now. So this would be a mission which would launch in the 2040s, get there in the 2050s. So I've got a new PhD student working on that for to provide some data analysis from Cassini, but also an instrument concept. So we're looking forward to that in the future. But it's the next generation which will take that on. But nevertheless, an exciting possibility. And so the trouble with the outer solar system, of course, is a long way away, and so you have to wait a little while. And then with the available funding, you're limited in what you can do in terms of sending missions to any of these. But this is what the current sort of missions are looking like. But the scientific community sort of come together and decide what the next mission is going to be, and try and sort of make it complementary with each other. So the Chinese sample return would be complementary with what's being done in the West, like the rover has been so far. So, you know, it's a big international community. We have in a few weeks the big international conference with all the space agencies involved, which is called COSPAR. That's going to be in Korea. So this is something which I'll go to and present some stuff at, but it's also a chance to talk to the international colleagues. So all of these conferences going around in the world, we compare data, and we're doing it for humankind. Yeah.
Thank you. In the context of Rosalind Franklin, what would proof of life on Mars look like? I mean, I'd like a picture of a little microbe, but what will I really get?
Be great, wouldn't it? Yes, if we could have a fossil or something like that, it'd be fantastic. But the reality is we're looking for chemical signatures, and so it's things like complex hydrocarbons and nitriles, but also so amino acids and things like that. Phospholipids, and so those are involved in cell wall boundaries. So it's those sort of developed types of. So it's chemical proof rather than visual proof. We'd be very lucky if we were to get some visual proof of that type of thing, or fossils underneath the surface or something. But you know, we can look. We'll have pictures, so we can take a look. But the most likely thing is primitive life could have started there, but then probably stopped. And so we're looking for those biomarkers. There are signs of ways of preserving that, by the way, on the surface as well, which are sort of quite interesting. So the Curiosity rover found a couple of years ago that you can actually sometimes in rings, in the benzene rings and hydrocarbon rings, you can substitute a sulfur, and that means that it's easier to keep on the surface. So we're looking for that type of evidence, the sort of chemical evidence rather than physical evidence of actual signs of life. But that would be, you know, if we discovered that anywhere else in the solar system, that would be amazing. Of course, with any discovery like this, it would take a lot of discussion in the science community to convince people that it's correct, and then, you know, you'd like ultimately to do a couple of different measurements and make sure that is correct as well. It's like, you know, the Higgs boson, you have to have a couple of different experiments to cross-check on each other. So it's a little bit like that with the different missions. And so, but if we have chemical signs of life, that would definitely be a Nobel Prize in that.
Hi. So you showed a brief drawing of like an outcrop, which you use PanCam to look at, and then deciding where to drill.
Yeah.
The material that you were hoping to get into, the outcrop indicated, between that, was that sort of more sandy material, and then you're looking at what kind of material is that outcrop made from that you're looking for? Yes,
you're looking for places that you can get a sample from underneath the surface. So you're looking, if you see an outcrop on the surface which gives you particular promising looking samples, then it will be better preserved underneath the surface where you have all the dust and so on, which has been left there for many years. And so the radiation, the idea is it's preserved better. So it's a more pristine set of material that you would get then from when you drill underneath the surface. So, yeah. Okay.
How long do you expect the Rosalind Franklin rover to be operational for?
It's about 5 months, I think, on Earth. But is that right? Several months, anyway. It's 200 and something souls on Mars is the design lifetime. So a matter of months, and so during that time, we hope to do, to rove around to some extent, but also to decide with the instrument where to drill and to do at least 2 really deep drills and some less deep drills as well, and analyse those results and send them back. So, but yes, a matter of months. So having said that, previous rovers which have gone to Mars, I mean, we had Opportunity, which landed in 2003, which was the same landing opportunity that we had with Beagle 2. Unfortunately, Beagle 2 did land successfully, but didn't send us the data back, which is a real pain, to say the least. But it unfurled all except one solar panel, and then but you needed to do the last one to get the transmission back to Earth. But Opportunity, which landed at the same time, that lasted I think 14 years on Mars, way beyond its design lifetime. So if you can get through the entry, descent, and landing onto the surface, then likely the engineering is good enough to survive for quite a long time. So with that, it survived many dust storm seasons. It was eventually a dust storm which killed it in the end, but nevertheless, it did survive lots of dust storm seasons and so on the surface of Mars. Dust does build up, but it blows off in the wind and also moves off with a rover moving around. But the student, last but one, the one that finished a couple of weeks ago, she was looking at dust storms and how those affect actually the upper atmosphere and the sort of magnetic environment of Mars, boundaries in that upper region. So that's sort of where the effect of the dust storm can not only be on the surface but also out in space as well. But yeah, a few months basically is the answer to when the lifetime of the thing. Yeah. Planned, yes. Yeah.
In terms of PanCam's capabilities, if again there was no limit to what you could add on there, is there something missing that you would have liked to have seen there that it could do?
Well, I mean, we have a science traceability matrix, which means we have decided some science questions and the resolutions and so on which we need to be able to answer those questions. So we can do everything that we needed to. However, if we were starting again, yes, of course, we'd use much bigger detectors and much, we did experiment with hyperspectral imaging, but you can't really do that on the surface. We did try some experiments on that. We can't do it, but yeah, there are things one could do which were better, but we have enough to be able to answer the science questions which we have, and especially where to drill. That's the sort of main thing, to do that choice. So we have enough to be able to do that. But yes, if we started again, we definitely use bigger detectors.
I mean, it was supposed to launch such a long time ago as well,
yeah.
Right? So now technology and so forth is moving on. And
you're absolutely right. Yeah, because our detectors, they're 1 megapixel detectors. So in a mobile phone, obviously, you have maybe 20 these days or something like that. But of course, you can't send a mobile phone to Mars, and you can't send the detector in it to Mars either. But there are bigger chips, 2 and 4K chips which you can use and so on, which we have used some of them on, for example, the Euclid spacecraft and all that. But having it robust enough to go to the surface of Mars and do its measurements, we have what we've got for the moment. And the UK Space Agency has been very generous with the funding, but I think doing any changes at this point would be difficult. Plus, we've ranged all the data. The whole system is designed to cope with that. So yeah, we couldn't really do anything in a short time. What we can do is NVIS and fill the space, and that's why it has to be exactly the same. The mechanical and also the electrical interface and the harness and everything and the data rate all has to be exactly the same as it was going to be for ISIM. So that's a challenge in itself. So doing something beyond that would be difficult at this point. We have enough with the current hardware to do what we want and to give the science of the whole mission. And it's the combination of instruments, of course, working together, which gives you the really exciting science which we hope for.
In that respect, obviously, Perseverance was kind of a Curiosity Mark II.
Yeah.
Do you think that ESA would approve a second rover if this is successful?
I think so. I think it was originally we wrote the proposal for this actually back in 2003, so it's over 20 years ago now. And I look back, we had a little 2-page thing which we had to put in at the time, and So yes, they would. However, we need to get this one there first and show that we can land and all that, because of course there have been other difficulties with landing which ESA has had. The Schiaparelli didn't quite, land.
Lithosphere braking, I think it's called.
Pardon?
Lithosphere braking,
Yes,
I believe it's
yeah,
called.
exactly. That's right. That's what it did. So, which was very sad, of course, and I think it was, the computer system got confused about the signals coming in and thought it had landed, but it was still several kilometres above the surface, and it just, there we go. But however, yeah. So showing we can land. And I'm sure, yes, definitely we will need to go back for more. But by that time, the scientific landscape may have changed with what Perseverance finds on the surface now. Also, if Mars sample return happens, whether we get that sample back in time to be able to then react to, and also what the Chinese mission finds. So all of this is really exciting for the international community. Yeah.
Thank you.
Yeah.
Actually, I have a quick one. Where and how are these bespoke filters made? These 22
okay.
filters?
So these are, we had to define the wavelengths. They're commercially available, but and I think it's somewhere in the west of England. I can't remember exactly the firm, but yeah, it's in the UK. Yeah. Interference filters, and we have to be very careful because actually, if you go away from the sort of middle of it, the wavelength that you're looking at changes a little bit because of that thing. So we have to be careful when we're doing that solar imaging that the sun's disk is in the very middle of the image. So it's an interesting question. Yeah.
Jeff Bryant asks, if there is no evidence of signs of life discovered on Mars, would that prejudice future missions to the moons?
Well, yeah, it's an interesting question. I mean, we're looking at them both at the same time, of course. We're looking at Mars and looking for things, and then the outer planet moons. There's these current missions which are planned, including ESA's long-term one. So with those, we would hope to find habitability with that. So if we don't find life on Mars, I think the jury is still out for places like Europa and Enceladus, and so these are potentially interesting places to look at anyway. So I think if we didn't find life on Mars, again, it might be that we're at the wrong point or something, or we haven't looked at the right thing. I mean, there is, of course, the question of should we send humans to Mars. I mean, this is another interesting debate point, and as to whether, before we find evidence of life, if we think life is there, should we be taking humans and all the sort of contaminating elements? So I have a personal view on this, which is no, not for now, but let's wait until we know. But no problem out using the moon, and I know Jerry would argue with this point. But using the moon, absolutely no problem. But Mars, for me, let's keep it robotic for now. Yeah, it's another point.
It reminds me that I forget when it was. It was when the Mars rovers, the first one, Spirit and Opportunity, they'd been on the surface for about 6 months, and Steve Squires, who was the head of the project, gave a presentation at the Open University.
Oh, yeah. Mm-hmm.
And I just asked him how long would it take for astronauts on Mars to have done the same amount of work, and he immediately said 3 days.
Yes. He said this in his book as well. So he wrote a book about Spirit and Opportunity and did this exact thing. But yes, I know it's much more efficient, of course, to take humans. But the trouble is you have all the contamination issue.
Right. Can I ask you, can you go back to the slide of Rosalind Franklin? Because there's something rather interesting in her notes.
This one. Oh, that Rosalind Franklin one. Yeah. What was that? here. Yeah.
Right. Okay, so we can see her notes on the photo 51. Would you like to say anything about this?
Well, it looks like life,
It says
doesn't it? I guess.
therefore helix,
Yeah.
and she's obviously
Made the
referring
link
to that,
made the
but-
thing to potentially the link to potentially life. And 4 chains. Yeah. So this is, I think, in the Wellcome Library, and there's a
Yes.
Wellcome Library website, which is where I got these images from. But yes, an interesting observation, though. Yeah.
Yes, indeed. Right, well, if there are no more questions, I'm sure you'd like to thank Andrew for a fascinating and entertaining presentation, which has given us so much to look forward to in the coming years. Andrew, thank you very much indeed.
Thank you.
And now I'll hand back to Andrew, Alan to finish off.
Okay, thank you very much indeed. Thank you, Andrew, once again, and thank you, Jerry, for organising that. Absolutely fantastic. Okay, just a couple of announcements. I won't keep you too long here. Just to say that our next meeting here is in September. It was going to be Roger O'Brien talking about Anglo-Saxon astronomy, but he discovered that hardly any took place, and it would only be a 5-minute talk at the most. So he decided to change that to distance scales. So he might do the Anglo-Saxon bit as well as a prelude to the other bit, but just let you know, a change of programme there. Couple of more dates for you. July the 6th, Saturday, July the 6th, if you would like to come and join us down at Wheathampstead. We've got their Carnival Day. We can put a stand up there, get some telescopes out, promote the club, show people what we get up to. And if you can't do that one, well, perhaps September the 7th, when we're aiming to do a promotion in Welwyn Garden City. We've asked the Howard Centre if we can go inside there, but we're also trying to ask the town centre management whether we can go in the outside bit, trying to cover our bases just in case the weather isn't so good. Let's hope by then that we're protecting ourselves from the sunshine. You remember that, don't you? Okay, well, thank you very much indeed for that. I would like to say, those of you, if it's your first time visit to us, I'm sorry, I'm moving around, Steve. If it's your first time visit to us, do come and say hello to us. We do like you to think, you know, that we are a friendly group, and we do like talking about astronomy. Doesn't matter whether you're a beginner or advanced, anywhere in between, or if you just want to talk about something else altogether, just come and say hello to us, and we hope that we will see you come to other meetings. And so to all of you, thank you very much indeed for coming along, to our speakers this evening, Andrew and to Martin, and to all the committee for putting everything together. And may I wish you all a very happy summer holiday, and we look forward to seeing you in the future. Thank you very much for coming, and good night.